Welcome to the deep dive. Today we're looking at a really fundamental lab technique, recrystallization. It's all about taking something, well, maybe a bit messy, a solid mixed with impurities, and getting something pure out of it.
Exactly. It's a powerful way to clean up solid compounds. And
Mhm.
our mission today is basically to unpack how it works step by step and what's happening, right down to the molecular level.
It sounds like chemistry magic, but I guess it starts with something basic, solubility.
It absolutely does. Solubility is the foundation. Think of it like this. How much of your solid, the solute, can you dissolve in a certain amount of liquid, the solvent, at a given temperature? There's a limit.
Okay, and the old rule, dissolves, that still applies here, right?
Right.
Polar stuff and polar liquids, nonpolar and nonpolar.
Precisely. Oil and water don't mix, and the same idea works for dissolving solids. But here's the crucial part for recrystallization. Temperature.
Ah, right. Heating things up usually makes things dissolve better.
Generally, yes, especially for solids. When you heat the solvent, the molecules get way more energy. They start zipping around faster. This allows more of the solid molecules to break free and dissolve. So hot solvent can hold much more solute than cold solvent. That difference is what we exploit.
Okay, makes sense. We load up the hot solvent with our compound and the impurities, then we cool it. Why does the pure stuff crystallize out, but the impurities don't?
Well, it's pretty clever, actually.
Right.
As the solution cools and becomes saturated, the molecules of your desired compound, they're all identical. Remember, start finding each other. They organize themselves into a really neat repeating pattern. That's the crystal lattice.
Like building with identical Lego bricks.
That's a great analogy, yeah.
Yeah.
And because the impurity molecules are different shapes, different sizes, maybe different polarity, they just don't fit into that perfect ordered structure.
So the crystal structure itself kind of pushes them out.
Exactly. The growing crystal actively excludes them. It's like having the wrong key for a lock. So the impurities tend to stay behind, dissolved in the cold solvent.
Fascinating. Okay, so knowing that, the first big step must be choosing the right solvent. This sounds tricky.
It is. It's maybe the most critical choice. You need a solvent that does almost nothing when it's cold. Your compound should barely dissolve at all near, say, 0 degrees Celsius.
Okay, bad when cold.
But it needs to be great when it's hot. Your compound should dissolve really well when the solvent is boiling or close to it. And a couple other things. It shouldn't react with your compound, obviously, and ideally it has a relatively low boiling point so you can evaporate it easily later.
Right, you don't want it sticking around. So bad when cold, good when hot. Got it. Step 2 then, dissolving.
Yep. You add your impure solid to the chosen solvent in a flask, and you start heating it, usually to boiling. And here's a key point. Use the minimum amount of hot solvent needed to just dissolve the compound.
Why minimum? What happens if I just pour loads in?
Well, if you use way too much solvent, then even when you cool it right down, your compound might just stay dissolved. You won't get any crystals back, or very few. Your yield will be terrible.
Okay, minimum hot solvent. But what if some stuff just won't dissolve, even when it's boiling, like little bits of sand or something?
Good question. Those are insoluble impurities. You need to get rid of them before you cool the solution down. And we do that using something called hot gravity filtration.
Hot filtration, so keeping everything hot is important.
Absolutely crucial. You use a short stem funnel, maybe some fluted filter paper to make it go faster, and you filter the boiling solution. If it cools down during this step, your desired compound might start crystallizing right there in the filter paper. That's a mess.
Right, you lose your product. Okay, so we've dissolved it, filtered out any insoluble junk while it's hot. Now, step 3, cooling. I hear patience is key here.
Patience is definitely a virtue. Slow cooling is the goal. Think about it. You want those molecules to arrange themselves perfectly into that crystal lattice we talked about.
The Lego bricks need time to click together properly.
Exactly. If you crash like sticking it straight into an ice bath, things happen too fast. The lattice forms quickly, maybe trapping some of those impurity molecules inside. Fast cooling generally gives you smaller, less pure crystals.
So let it cool slowly on the benchtop first, then maybe an ice bath later to maximize the yield.
That's the standard procedure, yes. Let it reach room temperature slowly, then use ice to get as much solid out as possible. Now, sometimes nothing happens. You wait, it cools, still clear.
Uh-oh. What then?
Don't panic. A common trick is to gently scratch the inside bottom of the flask with a glass rod. That tiny scratch creates a rough surface, a nucleation site, where the crystals can start forming. Sometimes that's all it needs.
A little nudge to get things going. Okay, so we've got our nice crystals sitting in the cold liquid. How do we get them out?
Step 4. Collection.
Oh.
We use vacuum filtration, usually with the Buchner funnel and filter paper hooked up to a vacuum source. It sucks the liquid through, leaving your crystals nice and collected on paper.
And then we just dry them.
Almost. One more important little step. Washing. The crystals, even though they're pure inside, are still wet with the leftover liquid.
Ah, the liquid that still has the impurities dissolved in it?
Exactly. We call that the mother liquor. You need to wash the crystals with a tiny amount of ice-cold solvent. Cold, so you don't dissolve your precious crystals, but just enough to rinse away that impurity-laden mother liquor clinging to the surface.
Okay, a quick cold rinse. Then finally, drying and weighing.
Then you dry them thoroughly, air dry, oven, desiccator, whatever's appropriate, and weigh the final pure product. This lets you calculate your percent recovery.
Right, like if you started with 3 grams of crude stuff and ended up with 2.4 grams of pure crystals.
You do 2.4 divided by 3.0 times 100. That's an 80% recovery. You almost always lose some product because a little bit will always stay dissolved in the cold mother liquor. That's the trade-off for purity.
It's a necessary sacrifice, you could say. You lose some mass, but you gain purity.
Precisely. It's a purification technique, not just a recovery technique.
That actually leads to a great final thought for you, our listener. If you did this whole recrystallization process, you followed every step perfectly, but you got 100% recovery back. What might that actually tell you about the sample you started with?
Yeah, think about that. If nothing was lost to the mother liquor, were there really any impurities to remove in the first place? Something to ponder. Purity usually comes at a small cost.